Sure.
Okay. So the second talk of this morning will be the second talk given on dynamical zeta functions by Mac.
Thank you very much. So in the first lecture, I tried to set the scene by talking about very classical zeta functions. The first one was the most classical, which is the Riemann zeta function, which of course is defined in terms of prime numbers. And so it's defined as an Euler product. And here S is a complex number, it's our complex variable. And one of the famous applications is to the prime number theorem that gives us an asymptotic for counting the number of primes up to a length x. So this is all very classical number theory. And then I mentioned this analogous setting, which was for graphs, where you take a graph, fixed graph, let's say just unorientated for the moment, and then we look at loops in that. There's a countable set of things in the same way that there were a countable set of prime numbers. The weights are now the lengths, the number of edges or vertices you pass through on a loop. That corresponds to the value that you're interested in counting. And the appropriate object that keeps track of these is in this case, the Ihara zeta function. So it's a complex function, again, given as an Euler product. The product over all the closed loops, and the thing you take a product is this object. So z is a complex variable, so it's a complex function. And by analyzing its domain in the same way that information about the domain of the Riemann zeta function gives you information about the objects you put in. And in this particular case, there's some corresponding asymptotic. So one feature of these two examples is they're not very dynamical. So since I want to talk about dynamical zeta functions, we should move on. And in this lecture, my plan is to talk about the generalization from this to something to do with geometry. So in particular, I now want to talk about surfaces. And so in this case, what will happen is we will have a compact, probably, surface, which in deference to being in France, I will call V. And then on the surface, well, the loops over here are going to be replaced by curves on the surface. In this case, they're going to be, in fact, closed geodesics, which I hope I will consistently call something, gamma. And here, the length is just the number of vertices you went through, or the number of edges you went through. And here will be the geometric length on here. So this will be of length L of gamma. And so the plan is to fill in these two things and say some more stuff. And so the corresponding zeta function here will be the Selberg zeta function. And I'll fill this in a moment, not having left myself much space. And in order to do that, let me just introduce some notation. So this will be the next section, which will be on the Selberg zeta function. So Selberg was a very famous number theorist, and in the mid-1950s he introduced this object. And so the context I'll consider for simplicity is the following. I'll let V, this guy, be a compact surface. It's actually a Riemann surface, but let me just put surface for the moment, of constant curvature kappa equal to -1. So that's my hypothesis on this surface. So if you're not a Riemannian geometer and you're not very comfortable with constant curvature surfaces, the easiest way to think of it is probably the following. But if I take my surface, for various reasons, the assumption that it's got curvature equal to -1 means that it can't be just a one-hole torus, and it can't be a sphere, but it has to be a surface of higher genus. And in this case, one way to think of this is to introduce the disk. So I'll let D be the unit disk. Z is equal to x plus iy, with the property that the absolute value is less than 1, so this is just a unit disk. And then the unit disk is actually a cover for this surface. And that means that you can find a local homeomorphism which maps me from here to here. And moreover, we can arrange that this is actually a locally isometry. So we can let this have a particular metric. So with the Poincare metric, and the way to write metrics usually is that a small distance looks a bit like Euclidean distance, so x squared plus y squared, but then it scales a bit, and in this case it might scale by 1 minus the absolute value of z squared squared, something like that.
ds squared.
Sorry?
ds squared.
ds squared, thank you very much, yes, that's correct. Yes, so if it wasn't that, then it would look an awful lot like Euclidean space, because it would just be the usual Pythagorean thing. And the thing on the bottom simply means that if you start at the center of a disk and you progress it to the boundary, then this thing gets bigger, and so your distances get larger. So it's the mystery of hyperbolic space. Okay, and so this is a metric on the Poincare disk up here, and if we take the surface downstairs, then we can lift it locally to some region up here, and the metric that it has here just inherits this metric from here. It just looks the same locally. So there's no mystery involved. We're actually interested in closed geodesics. So closed geodesics are just closed curves on the surface, which are actually locally geodesic. So between any two nearby points, they minimize the distance. So it's a bit like an elastic band sitting on the surface. If we had a surface of negative curvature, and then it's just the shortest curve to which you can deform a given curve in this way. And there's a simple geometric fact which says basically the following, that in fact if you're given a closed surface, then there in fact is a countable infinity of closed geodesics. So there's infinitely many and it's countable. There is a countable infinity of closed geodesics. So I succeeded in drawing one. It doesn't look much like a geodesic. There is. It doesn't look much like a closed geodesic, but it's supposed to be. And there are more on this surface, so probably there's one that goes around here. And there's probably more complicated ones that go around in different ways. And if you keep making them up, there'll be infinitely many. And in fact, you can prove this there's infinitely many because if you look at the fundamental group of this surface, it grows at some particular exponential rate. And in fact, there are infinitely many things in it. And each of them has to contain a closed geodesic. And moreover, there can't be uncountably many because in every free homotopy class, that's every conjugacy class for the fundamental group, there can only be one. And you can see that simply by lifting stuff to the universal cover. So it's some reason for it to be true, and it's true in this particular case. For constant negative curvature, even variable negative curvature, we have the property that there are countably many geodesics. So if you were to plot them on the real line, here's 0, you just put notches at all of the guys. It's analogous to what happens with prime numbers, except now these are just numbers which are lengths of different geodesics, etc. So we try to pursue this analogy. And then it brings us to the definition. So this is the definition of the Selberg zeta function. Okay, so you might imagine, well, you would imagine correctly that we're going to define something using these numbers in the same way we did for the primes and for the lengths of the curves. You might imagine that we're going to do something very similar to this, but we don't. We do something slightly different. So let me write the definition down and then say what it is. So before I do that, let me just remind you of this notation. I'll let gamma denote one of these infinitely many geodesics. So it denotes a geodesic of length L of gamma. So there's infinitely many of these, countable infinity, and then we'll use these to do the following. So here's the definition. It's the definition of the Selberg zeta function. So the Selberg zeta function is defined by the following. Well, it's going to be a function of a complex variable in the same way that the prime numbers were. To distinguish it from this, I'll use the classical notation, which is to write z instead of zeta. It's okay so far. It involves an infinite product over the closed geodesics in the same way that the closed loops appeared over there. And then it's 1 minus e to the minus s, I'm going to put something in a minute, times L of gamma. But the difference here is that we're also going to put another product in, which hopefully will show up, which is the product n equals 0 to infinity, and this should be n plus that. And I do not put a minus sign, minus 1 up here. So basically it looks more or less the same, except there are some changes. And when I write this down, sometimes I don't write it down in this form. I write it down in the form more analogous to the prime number theorem. But the reason I'm stating it this way is because this is a classical presentation, and it makes for tidier results, which will become apparent in a moment. So you could define the Selberg zeta function by complete analogy with this, but I'm not, for reasons that I hope will become apparent in a moment. Okay, so let me say some stuff. Oh, I should also say that this thing converges, providing the real part of S is bigger than 1. You can prove that just by some crude estimates on how fast these grow, but it should grow at this rate. Okay, what else can I say? Okay, it converges in some particular half plane, and in analogy with the other theorems, particularly the theorems on the Riemann zeta function, one would expect to say something about the extension of this function. I keep forgetting I don't need to keep my finger on the button. Okay, and so some of the main properties of the Selberg zeta function let me just remind you it's for any surface, compact surface V. You change the surface, it will actually, of course, change the zeta function. So, at the risk of slowing things down too much, let me just bring this down enough so that I can write a V here. I won't do it in future. It's just to remind us that if you have different surfaces, you get different zeta functions. But let's imagine we're given a surface, and then we look at the zeta function, and then there's a theorem which is basically due to Selberg from 1956, and it says that the following is true. First of all, zeta of S converges to an analytic non-zero function on the real part of S greater than 1. That's the easy part. So in the domain, here is 1, and so all I'm saying is that it converges to an analytic function to the right of this line, which is non-zero. And then more ingredients are that 1, it has an analytic extension to C. It's an entire function. You can extend it to the entire complex plane. in much the same way as you could the Riemann zeta function, modulo what happens at s equals 1. And at s equals 1, in the case of the Riemann zeta function, we had a pole. But because of the way this is defined, zeta of s now has a simple 0 at s is equal to 1. So this value, well, for the zeta function, the Riemann zeta function, it was a pole. Now it's a 0. Well, it's not much difference. It's not, maybe not so surprising since we didn't put a minus 1 at the top. And secondly, or thirdly, in fact, zeta of s has no more poles or zeros. It doesn't have any poles, in fact, on the line real part of s is equal to 1. So as in the Riemann zeta function, there's nothing else on this line apart from that particular value. So the statements are more or less analogous. They're not quite the same because it's a different object, but fundamentally it has this form. And let me just emphasize what I just said by saying, by way of a remark, this version of zeta of s follows the original historical version, historical form. Being a good traditionalist, I'm just writing it down exactly as Selberg would have done in these things. Does it say in my notes? Okay, and as in the case of the Riemann zeta function, if we knew some information about the zeta function only on this line, and the fact it converges on the half plane, that was enough to prove the prime number theorem. For the Riemann zeta function, we simply needed to know that there were no more poles or zeros on this line, a simple pole here, and it's analytic to the right. And in fact, the corresponding results here are enough to prove something about geodesics on the surface. If you worry about the fact that it's a simple pole, simple 0 rather than the simple pole, don't, because actually when you do the proof, you take the logarithmic derivative. And of course, when you do that, poles and zeros look pretty much the same because they will both become poles. But anyway, so the remark is that this is enough to prove the analog of the prime number theorem and the prime graph theorem. And so I'll call it theorem, let's call it the prime geodesic theorem. And when I say prime, it means because when I have a closed geodesic, I only go around it once. If I have multiple geodesics, I throw them away. I only take one route. So let me just say that. And if that worried you, don't worry about it because it's not important, in the following sense that if I look at the number of geodesics whose length, geometric length, is less than t, so for any t, this is going to be a finite number for any finite t, but it grows monotonically, and it grows monotonically like e to the t over t as t tends to infinity. So it grows at a well-defined rate. And I remind you that that simply means that if you take the limit as t tends to infinity of the number of geodesics with the property that the length is less than t, well, if you compare that with e to the t over t, then the limit's equal to 1. So if you look at the statement of the prime number theorem, it has x over log x instead of e to the t over t, but that's not very surprising because here we have the p as the on the same line, and in this case we have the lengths in the exponent. So, what can you expect? So that's the corresponding statement. So perhaps one of the reasons that the Selberg zeta function is kind of interesting, particularly to number theorists, is because it does satisfy the analog of the Riemann hypothesis, this promised holy grail. So let me just say something about that. And it's related actually to the Laplacian. And so I'll call this section the Laplacian and the Riemann hypothesis. So Riemann hypothesis is in quotation marks because it's not the Riemann hypothesis because it's not related to this zeta function but to the Solberg zeta function, and also because it's slightly different in a way that will become apparent in a moment. So let me remind you that we'll always assume, again, that V is a compact surface with curvature equal to -1, which we can think of as just taking the unit disk, folding it up by quotienting out by some appropriate group of isometries and giving us the surface at the bottom. And then we can let this delta denote the Laplacian. So this will be a map which is defined from L2 to L2 on the surface. So V in the previous lecture, of course, denoted vertices of the graph. Now it doesn't. It represents a surface. And I'll let this be the Laplacian. So it's a second order linear differential equation. And you can think of it on the unit disk because it corresponds to locally differentiating on the disk. So we can take functions upstairs if we wanted to. And here it corresponds to 1/4, would you believe, 1 minus the absolute value of z squared, squared, d squared, dx squared, plus d squared, dy squared. Anyway, it's some second order linear differential operator, which takes a function in here to a function in here. And so, since we don't like to differentiate L2 functions necessarily, we take smooth functions in here, and we just take the completion in the L2 norm. But it means something like that. And so, why does this operator make an appearance? Because it plays the role of this operator that maybe Polliott and Hilbert were looking for in the case of the Riemann hypothesis. And so, the following is a standard result. So we just put a standard result. So we have this operator acting on functions sitting on the surface, and in particular, the Laplacian is a self-adjoint operator. And so what that means in particular is that the spectrum lies in the real line. Which is important. So the claim is that the eigenvalues of this operator, its spectrum, are actually going to be relevant to the zeros of the zeta function. And so therefore, if we're interested in understanding the zeta function, in particular its zeros, and deducing stuff from that, the way to do it is to look at the Laplacian, because there's going to be a direct correspondence between the eigenvalues of this operator and the spectrum of the Laplacian. So just to complete the thing here, it should have been the Solberg zeta function is a product over closed geodesics, and also this extra product n equals 0 to infinity of 1 minus e to the minus s plus n times the length of the geodesic. And then the analog of this would have been the prime geodesic theorem, which says that the number of geodesics whose length is less than t is asymptotic to e to the t over t. You might wonder why it's e to the t over t and not e to some constant over something. And the reason is because we assumed a normalization for the surfaces. We all assumed they had minus curvature minus 1. If we'd chosen surfaces that had curvature minus 24 or something, then in fact the asymptotic would be different. There'd be a square root of 24 in front of a t. But we didn't, so it's not an issue. Okay, so let's write down the spectrum of the Laplacian. So I use the following notation. So it's a compact surface. So in fact, the constants are in L2. And if we differentiate the constants twice, we get 0. So therefore, one of the eigenvalues is just 0, the first one. And then there's a whole bunch of these guys. And because it's a compact surface, there's some reason that says these eigenvalues are going to be all we see. And they go off to infinity. And they are the spectrum of the Laplacian. So there are eigenfunctions called phi, such that this plus lambda n phi n is equal to 0. There's always some hiccup with the minus signs in these things, but this is the correct equation, I hope. And so here the phi n's are eigenfunctions. And the fact that the spectrum goes off to infinity, and in fact a rate for it, is given by the classical Weil's law, about which I will say absolutely nothing, except that it's an extremely nice result on how the eigenvalues increase. And the punchline to all this is that we want to say that the zeros of the mysterious Selberg zeta function are given in terms of these eigenvalues, which are lambda n equals 0 to infinity, for the Laplacian. And of course, the Laplacian itself depends on our surface V, something I'm just taking for granted. Okay, so what can we say? Well, after this rather long run-in, we can say the following. So here is the theorem. Maybe I should draw another picture. So this is the line. So this is the value s equals 1. This is the value s equals 0. There's going to be a line down here, which is the real part of s is equal to a half, which in the case of the Riemann zeta function is where we'd like to see all the zeros. But what can we say about the zeros in the case of this analytic entire function? Well, the zeros of zeta of s, the Selberg zeta function, are given by, well, I'll class them in the following way. Well, first of all, we've seen one of them. So s equals 1 is a simple 0. No surprises. A second one is that there are, the second class is there are countably many zeros corresponding to these countably many eigenvalues by the formula, which I think is 1/2 plus or minus I times the square root of 1/4, I'm not sure about the square root at the moment, minus lambda n. So they get big, they get imaginary, you take a square root, maybe that's not there. Okay, and where n is greater than or equal to 1. And these are the so-called spectral zeros. Which in English probably means they have some sort of ghostly presence, but in fact they're just there.
If n is equal to 0, did you again, if n is 0, you do s equal 1.
Yes, that's right. So you shouldn't read too much into when I write things exactly. There's always some intuitive thing in these things. So let me just leave it as it is, but you're quite right. So these spectral zeros, they occur on either this axis, corresponding to when lambda is small, hopefully. So there might be some guys down here, or there might not be. Sometimes there are, sometimes they're not. But otherwise, they're going to be on this line up here. And there's a geometric interpretation as to when the small eigenvalues occur, which I won't say directly. I might make a comment, but I won't write anything down. And the third is that there are some boring ones which just correspond to -1, -2, etc. So let me just say s is equal to minus m, where m is 0, 1, 2, blah, blah, blah. And these are what I'll just call trivial zeros. They're less interesting. Okay, so that's more or less how we describe the zeros, but the high point here is that the eigenvalues of the Laplacian tell you most about the spectrum, the zeros of the zeta function. And just by way of a remark, this is my justification for writing this more convoluted form of the Selberg zeta function, is because if we didn't write this, if we didn't have this infinite product here, we get the same picture but repeated. There's some cancellation that occurs because of this infinite product. So we get such a simple formulation because of the form of zeta of s. It's more a presentational thing, at least for me at the moment, rather than anything very profound. And the other remark I might make is that the Laplacian, as I said before, kind of plays the role of this mysterious operator. So the Laplacian plays the role of the operator of Pollier and Hilbert. Maybe Hilbert and Pollier sounds better. Let me just say it in words rather than actually saying it, writing it down, which is that if you were looking for surfaces for which these guys here, which kind of violate what you might call the integrity of the Riemann hypothesis, you might want there to be no zeros on this line. Well, these guys here correspond to certain kinds of surfaces. And geometrically, they correspond to long, thin surfaces for which there is a very narrow waist. And then using Cheeger's inequality and some geometric stuff, you can prove that there are small eigenvalues for the Laplacian. And by this correspondence, it means that you have poles which are zeros which are very close to this line. And if you have kind of short, stocky surfaces which don't have thin waists, then it can allow you to have just the zeros on this line. So there's some reason. Different surfaces give you different effects. However, what you do get out of this is enough to improve the basic asymptotic here, because, of course, the entire philosophy of the Riemann hypothesis is that it would imply better estimates on counting things. And so we don't know it for prime numbers, but we seem to know something like it for the Selberg zeta function, so therefore we'd expect to be able to get a better asymptotic, and of course we get that. So let me see what I've written here. So corollary. Well, let me write it as a corollary. So this is like the Riemann hypothesis. Well, at least we know that zeta of s has no zeros in a strip which is given by the real part of s between 1/2 and 1/2 minus epsilon. So here I can just draw a line down here, slightly to the left of this guy, right of this guy, of size epsilon, and so certainly in that region there's no zeros. Yes? Yes, you're right, it's 1. Thank you. It's 1 and 1. Right. And so with this assumption, then we can just carry out the previous analysis, and this implies that we get a better asymptotic, and what we get is that if you count the number of closed geodesics whose length is less than or equal to t, well, we know it has a basic form, which is it's asymptotic to e to the t over t, but we can do better than that. We can say that it's equal to some principal term plus an error term which will go like e to the t 1 minus epsilon, where this epsilon is actually slightly smaller than that guy. So that would be the error term. And the principal term would be the same order, but it would be written more formally as the integral from 2 to e to the t of du over log of u, which is not so complicated, but is itself asymptotic to e to the t over t. So we get a better estimate, get a nice principal term, and we get an exponentially smaller error term as a consequence of these properties of the zeta function. Let me make a remark about the proof, which I will not even attempt to say very much about, but the proof uses what's called the Selberg trace formula. Which is basically a black box for our purposes, and what it does is it takes geometric information, which is just the lengths of the closed geodesics, a countable set of numbers, and it relates them to another countable set of values, which are the eigenvalues of the Laplacian, and it's a correspondence between these things. So it has a very sophisticated and elegant form, which I will not attempt to explain. But that's how it works. I've made some comments in the notes, which I will try to clean up and elaborate. And if you're wondering what the word trace means, it corresponds to the fact there's another operator involved, not the Laplacian, but there's actually an integral operator. With respect to a certain kernel, and this is the thing which turns out to be of trace class, or at least it's a compact operator, and this operator is, as you might suspect, somehow related to it's a heat kernel related to the Laplacian. But let me not say anything about that. That's just in case you were curious to know why the word trace appears. It's a trace of something. So let me now walk off of this rather treacherous thin ice I'm using by talking about spectral theory, and instead let me say something about something more dynamical. So let's try to understand the Selberg zeta function in a slightly different setting. So here I've assumed that the surfaces were compact surfaces. What happens if we assume that they're non-compact? So let's assume that, in fact, they have infinite area. So this leads to a few complications. The first complication is that it's rather hard to use spectral theory in this setting, because if the surface has got infinite area, it's hard to look at L2 functions, because, well, you can, but it causes all sorts of complications. But there is a more dynamical approach, which I'll attempt to explain. And so this is a simpler setting. Let me put simpler because it's simpler for me, but maybe not for everybody. But it's also a more dynamical viewpoint. So let's just think about the definition of the Selberg zeta function for a given surface. And now I want to look at the following. I'll assume that V is an infinite area surface given by a pair of pants. We have to bless the Americans for this particular notation. I noticed that David Brothwick just calls it a three-funneled surface, which is, how many L's are in funneled? Never mind. Surface, which might be more prosaic. And so in this case, what happens is that your surface has got these kind of funnels. So this is meant to be an infinite surface, rather than a compact guy. And in fact, because of the geometry, you can choose closed geodesics like this that cut off the funnels. And so in particular, to all intents and purposes, we're interested in this region in between, which is a surface which has these three holes in it. So this is the thing we're interested in. So when I write V, I'm not sure if I mean the infinite area surface or I mean the surface with the geodesic boundary, but whatever seems more appropriate would be fine. And so in this context, we have a result. Again, it's, of course, of curvature equal to -1. And in this case, it comes about just by taking the Poincare disk, which has probably disappeared, and then quotienting it out by something else. I'll draw the picture for this in a minute because it's in the proof. But let me just tell you what the statement is. So in this context, we have the following. So theorem. There exists a value delta, which is between 0 and 1. This delta now replaces the 1 that we used to have. So in this picture, now delta is our magic number, and it's to the right of this that the zeta function converges, such that zeta of s converges to a non-zero analytic function. Okay, so it's analogous to what happened in the compact surface case, except in that case delta was equal to 1. Now delta is just some other number, which actually has to be strictly smaller than 1 for some reason or other. And the second property is that, well, zeta of s again has an extension to the entire complex plane as an entire function. So zeta of s has an analytic extension to the entire plane, just as the Selberg zeta function did, and more or less as the Riemann zeta function did as well. And the third property is that when you look at the value delta is equal to, s is equal to delta, so this is the s plane. Well, when s is equal to delta, it's a simple 0. So zeta of s has a simple 0 at s is equal to delta. So these properties are highly analogous to some of the properties of the Selberg zeta function. I'm not claiming anything about what happens to the zeros in this region. So in the case of the zeros, it's all very mysterious because the spectral theory cannot be applied here. The Selberg trace formula doesn't work. The method of extending in this case is completely different. It uses completely different dynamical tricks, which I will now try to outline. They're not at all difficult. It just involves introducing a bit of framework. And so I'll do that for basically the rest of the talk, explaining how this works. As with all results in mathematics, the secret is to know that it's not really complicated. It's just a matter of knowing where the results are and how to put them together. This principle does not apply to my car, which keeps breaking down, unfortunately. Okay, so in this context is this surface. We can use a dynamical proof. What's it based on? It's based on transfer operators. Due to David Ruel. So many years ago I used to call them Ruel operators, but then Ruel complained, and so I started calling transfer operators at his suggestion. So where does the dynamics come from? Well, it comes from the picture upstairs. It comes from the Mobius transformations. So there are certain Mobius maps floating around in this picture, or at least there will be. And the idea is that we can describe our surface as being the disk with certain identifications. And here the identifications are given by a group. So if you had a flat torus, that's the usual standard torus in the plane, it would be R2 quotient Z2. here it's going to be the disk quotient something else, and it's the group generated by two transformations, A and B, where A and B are maps from the disk to itself. They're actually the Mobius maps. And the picture here is the following. So this is my surface. I'll draw it again maybe. So it's an infinite area guy looking like this. It does have these geodetic boundaries, which I don't need for this picture. And the way to think of that is that we have a disk, and within this disk there are 4 curves. 1, 2, 3, 4. And there are transformations which map one curve onto another. Maybe not that way round. Maybe this guy will be called A, and this guy will be called B. So these are both, they're just linear fractal transformations. They preserve the disk, and this curve is mapped onto this curve, and all of the space outside here is scrunched up inside there, and all the stuff inside here is spread out. But the arrow maps means that this map maps this curve onto this curve. These curves are actually meant to meet the boundary perpendicularly. And there are, if we have a picture like that, and we identify by the group this generates, then it gives you this surface. So it's a standard construction in this sort of thing. So the surface here, which was called V over there, is really just the disk with these identifications. You roll up the space, a bit like folding a blanket. Actually, nothing like that really. And then this is the picture you get. So you might ask, well, where do these mysterious curves here, which I'm identifying things, come from? And the answer to that is the following. They're actually what are called isometric circles for the two Mobius maps. The word isometric circle is a bit misleading, but let me explain why it's called that. So our starting point is to think of our surface V as just being the disk quotiented out by the group generated by two of these guys. And so the actual picture comes from these so-called isometric circles, which I'll put in quotation marks just to reflect the fact I don't like the notation very much. And how are they defined? Well, they're defined in the following way. Historically, they're called C, presumably for circle. And C of A is meant to be, I think, those points in the disk, presumably in the interior, but it doesn't make much difference, with the property that when we take the derivative of the map A at that point in the Euclidean sense, then that's equal to 1. So we take the Mobius map, so it's just a linear fractal transformation. We take the derivative in the complex inside the disk, and where the derivative is equal to 1 in absolute value, that describes my first disk. And so this guy at the bottom is actually C of A, this guy. And similarly, you can do the same for C of B. He will be all those points in the disk with the property that the derivative of B at Z is equal to 1. And so if my picture is anything reasonable, this curve here will be C of B. And you can carry on in this fashion. If you look at the inverses, C of A inverse will be equal to something you can guess, and C of B inverse will be equal to something you can guess. You just replace the A and the B by their inverses. They're just Mobius transformations. The inverse is also a Mobius transformation, and so it just gives us two more curves in the plane. And hopefully this would be C of A inverse, and this one will be C of B inverse. So now we have specific curves that are mapped onto each other by our two linear fractional transformations, which are giving us the surface originally. Right, and so a simple exercise, so in particular, we can check that the picture I've implied here, that this curve is mapped onto that curve, is actually correct. So if we use the linear fractal transformation, we apply it to the curve C of A, then it should be equal to C of A inverse, the corresponding curve. Similarly, B, C of B will be equal to C of B inverse. And unless I make some radically wrong mistake, maybe this is C of A inverse is equal to C of A, and B inverse of C of B inverse is equal to C of B. And this is just a simple exercise, just using the chain rule, just to check it. And hopefully it's correct, but it just says what the picture says. These particular curves, which are actually defined in that way, have this particular configuration. Okay, you may be wondering where the dynamics is. Well, in fact, we can use these to define some certain transformations. So the game is that we don't really care so much about the linear fractal transformations inside the disk. That's where the geometry is. But if we're good dynamical systems kind of guys, we're probably interested in maps acting on the boundary. This seems like a more natural domain to some people, so let's do that. And so I'll let IA, IB, IA inverse, and IB inverse, with Lumberson notation, be the associated arcs of the circle. Oops. So possibly A would have been a better notation for arc. I think I is meant to stand for interval, so I'm not sure that's so great. And what are these guys? Well, they're simply these regions here. There are 4 intervals which are just the interiors of these isometric circles on the boundary. And so the picture is much more evocative than anything else. And so in this picture, this would be I of A inverse. He's that blue arc. This would be I of B inverse. This would be I of B. And this would be I of whatever's left, A, maybe. Okay. Pause the thought. Anybody remind me when I'm supposed to finish? That would be useful. Noon. That's good, because that's what I was working on. Excellent. Okay, so now we have some regions, and it's on these regions that we want to define the transformations. Okay, and we can associate some maps. We can associate some maps. So the downside to this construction is you have to wait to find out why we're doing it, but there is a payoff a bit later on. And so I'll define the maps using the following notation. So T of A, for example, is going to be a map which maps us from probably IA inverse union I of B union I of B inverse. So it's 3 of these arcs in the boundary, and I think it's going to map us onto IA inverse. And how is it defined? Well, that's easier. We just apply the linear fractal transformation, which is hopefully A. Oops. A of Z. It's either A or A inverse, but the idea is that we're going to get this picture. Let me try to maybe erase something to draw a suitably evocative picture somewhere. How about here? So in the picture below, all that's happening is that I have a circle. I have these 4 blue intervals, or maybe arcs of a circle, which are this guy, this guy, this guy, and this guy. And then when I apply the transformation, what's happening is that this interval is mapped inside himself. This guy is mapped inside here. This one is mapped inside here. And that's the guy that I skip, give or take the notation. And I can similarly define TA inverse, TB, and TB inverse. So they're just maps on the boundary which reflect the action of the Mobius transformation. Great. What has this got to do with the zeta function? Well, the zeta function is defined in terms of the lengths of closed geodesics. And of course, the lengths of closed geodesics are intimately related to the group, which I've called gamma. And in fact, there is a direct relationship, just a calculation, which I can now just define. So if we're interested in closed geodesics, we can do it as follows. So for closed geodesics, so let's assume that we have an element of the group. So let's say this is an element G. So he's made up of generators, G1 composed up to G of n. So this is an element of gamma, which was generated by A and B. And here, all of my guys, G1 up to Gn are either A inverse, B, or B inverse. So I can write an element in the group in that form. It's probably better if I assume that it's reduced, which just means that when I write down a string of generators, I don't want an inverse followed by the same element. So i.e. gk for a typical term inverse is not equal to gk plus 1. And cyclically means that gn inverse should not be equal to g1. So it doesn't shrink in any reasonable or unreasonable way. So I can think of these guys, and then if I think of the associated transformations, well, there'll be a fixed point for the associated. So let x of g be the fixed point for the associated map. So it will be T composed itself several times. There'll be generators on the bottom, and it's going to be one way around or the other. Let's assume it goes that way around. And so we'll be looking for a fixed point for this map. So we have an element of the group. We assume it's cyclically reduced. We can associate to the generator's transformations. We look at the composition, we look at the fixed point, and then there's a simple lemma that says the following, that G corresponds to a closed geodesic. It's actually an axis for one of these guys with length L of gamma, so closed geodesic gamma, with length which is given by minus log, let me call this thing T of G, with log which is going to be T prime of G at the fixed point which I've called X of G. Okay, so all that's saying is that I take an element of what is in fact the fundamental group for the surface. It's this group generated by these two guys. I look at the associated action on the boundary given by these transformations. I look for fixed points for some given product of these guys, and then from that I can just write down immediately the length of a closed geodesic. So it's just a simple calculation. Everything is just an easy calculation. And it means that I can now think of all of the closed geodesics on this non-compact surface just as being coded, if you like, by strings of A's and B's. And then to get the length of the geodesic, I just look at the derivative of this map on the boundary. So how does any of this help us? Well, because we can now invoke an operator which will collect together all of this information in some easy sort of way. And this is the aforementioned transfer operator. So the transfer operator is, as the name suggests, it's an operator. It's a linear operator. It's not the Laplacian, it's something else. And it's an operator associated to these contracting maps, or these maps on the boundary, which are called TA, TB, TA inverse, and TB inverse. And so it looks very straightforward. And so it's defined in the following way. So this is going to be transfer operators. And the idea is that we want to define a Banach space, and we want to define a linear operator. So far, all we have is a disk, some maps, and a bunch of intervals, arcs on the boundary. So here are my arcs again. That's not in exactly the same place they were before, but there's 4 of them. And to define the Banach space, well, we choose small neighborhoods with a U. So small neighborhoods UG of each of these intervals I of G for each of the 4 choices A, B, A inverse, and B inverse. So these are just neighborhoods in the complex plane. So I choose some neighborhood around here, some neighborhood around here, some neighborhood around here, some guy along here. So that might be, say, U of A, U of A inverse, U of B, and U of B inverse, something like that. And let's let U just be the union of these guys. So just a collection of these 4 neighborhoods. So where's the Banach space coming from? Well, it comes as follows. I'll let B be the space of functions from this union of 4 regions I've drawn, and these will be functions which are analytic and bounded. And to make it into a Banach space, I have to put a norm, and the norm is simply going to be taking the supremum of the values. It's a bounded function, so we just take the supremum of the values of the function inside the neighborhood U. So this is surprisingly, it's a nice Banach space. You can also look at L2 functions if you feel inclined, but let me just stick with this. So this is a Banach space. I'll define the operator, and we've already had some hint that it's going to be relevant to the rest of the problem. So let me just say what the operator is. And since it's, I think there's enough room to define it here. So we can define well, in fact, it's a family of operators. Indexed by, in fact, our complex variable. And so these operators are defined in the following way. So it's L subscript S from the Banach space to itself. And how are they defined? I think I do need to put it on a new line. So it's defined using these transformations on the original intervals IA, IB, I inverse, and B inverse, but extended to the neighborhood U. So let me just write that down. And so formally it's the following. It's a linear operator. It has to act on some function. So W is going to be just an element of this. It's an analytic function from the union of these disks into the complex plane. It's going to give us a new guy, so Z will just be some element of the space. And so it's going to be defined by taking a summation over some of the elements. So let's say we take 3 of them, and the one we skip is going to correspond to where Z is. And then what we do is we take WG of Z. So we just move this, G should maybe be T of G of Z. I keep losing my notation. And so then it would be e to the minus s, the log of a derivative of the map at the value possibly z. Let's hope for the best. That might be right. So it's something that looks a bit like that. And here, this is where z is an element of probably u of g0. Okay, so the original transformations were defined on 3 of these regions into one of them, so we're skipping one of them, depending on where our point is, and hopefully this is a well-defined object. It's a bounded linear operator. And then the key to proving stuff about the zeta function is, first of all, to prove spectral results about this linear operator. It's a bounded linear operator on a Banach space, and then to relate them to the zeta function. So that's the final step, which we've arrived at. These are the spectral properties. And we can roll out a theorem, which is due to Grothendieck. This is prior to him working out Étale cohomology and farming. This is from 1955. And it says that the operator, well, L of S, and their powers, which is not so surprising. Well, the operators turn out to be compact operators, so they have a very nice spectrum. In fact, they turn out to be trace class, which is even better. So in particular, it means that there are only countably many non-zero eigenvalues, countably many eigenvalues, and they sum in some suitable way. So this is a nice classical result.
For all values of S? Or?
For all values of S, it's true, because in this case, it's only a finite sum, wherever the operator is. It's just 3 things being summed.
Oh, it's a finite sum.
It's a finite sum, yes. This is because we've chosen a nice example. So it's a very simple, it's obviously just a linear operator, and it's not very difficult to prove this. And it's the analyticity that makes everything work in this particular case. And then the connection with, so that's the lemma of Grothendieck, and the connection with the Selberg zeta function, connection to zeta of S. Well, this comes from a more recent result, more recent in the sense of 30 years ago or so. And this is due to Ruel. And what it does is it gives an expression for the zeta function basically in terms of these traces. And so let me write it in the following simple form. So this is lemma. And let's say it's due to Ruel from 1976. It's not exactly in this form, but it's equivalent. We can write that, well, if the thing is of trace class and its powers are of trace class, what are the tracers? So this is Ls to the n. So trace here just means sum of the eigenvalues of the nth power of the operator. So here I'm assuming that this is for any n greater than or equal to 1. Well, it's just some expression. So you sum up. The n here relates to the fact you're looking at compositions of n elements. So that would be g is equal to g1 up to gn, cyclically reduced. And the g1 up to gn, again, are just a's and b's, A inverses and B inverses, as they were up there. If I felt ambitious, I could write it as a subshift of finite type, but maybe I won't risk that. And then maybe it's going to be e to the minus s, the log of the derivative, so this is a map, g prime of something. So this was just a map I got on the boundary by compositions of these guys, and then I evaluate it at the fixed point I had before. The fixed point for these compositions. They can track, so there's only one of them. And then, unfortunately, there's also a term on the bottom, which is 1 minus tg prime x of g. So if you don't like so much the dynamics on the boundary, then according to the previous correspondence, this thing is pretty much like e to the minus s, the length of some geodesic, over 1 minus e to the minus the length of the geodesic. So that's what it corresponds to in some particular coding. And moreover, the zeta function makes an appearance in the sense that when you put it together, the Selberg zeta function defined before can be written in this sort of discrete dynamical way as the exponential of minus the summation n equals 1 to infinity of 1 over n, the trace of ls to the n. So the trace here is just the expression above.
Now S is somewhere.
Yeah, so if this thing is formally defined, of course, if the real part of S is greater than 1 to get it converged, but the content of the theorem is that this has an analytic extension to the entire complex plane. And yes, it should be delta. Of course, delta is smaller than 1, so I'm still safe, but in interests of accuracy, let me put delta. And then the point, of course, is that, so the idea, of course, is that, well, if you have an operator which is trace class, it's pretty much like a matrix. Matrices only have finitely many eigenvalues. Now we've got countably many, but they go to 0 pretty fast. And it's like the matrix identity which you can probably guess, because I haven't written it down, you may have to guess. Determinant of I minus z times a is equal to exponential, if it's the right way round, minus the summation n equals 1 to infinity, z to the n over n times the trace of a to the n. So the thing that you see for graphs and matrices is some identity a bit like that. And all we're doing is replacing the a by L of s and setting z equal to 1. And how can we afford to do that? Well, we just invoke these guys. And they tell us that we're in pretty good shape. So we've bypassed the spectral theory, and we've ended up with some particular method of extending these things using the Ruel transfer operator. Let me just make one final comment, and I think it's a final comment. I've got lots of comments, but I'll make a final comment now, which is that I said before that we're not using the Selberg trace formula, so we can't say anything else. We have an extension, but we know zip about it. We don't know, for example, where are the zeros. Well, we know there aren't any to the right of the real part of s is equal to 0. We know there's one at s equals delta. And we know that there aren't any more on the line, but we know very little more than that. And it's quite hard to find them, because if we're looking for zeros, we have to look for solutions where 1 is an eigenvalue for this operator. So 1 is an element of the spectrum of LS is equivalent to s equals 0. But it's not a very promising form because the operator is not so attractive. And so it's very hard to prove things. And I went to an excellent conference last week where there was a most excellent talk by David Brothwick, and he presented lots of slides using lots of computer time where he plotted zeros for this complex function in the critical region between a real part between 0 and delta. And he plotted it up to 1,200 in the imaginary direction. He has extremely attractive pictures. And having no shame, I've stolen some of them and put them into my notes. And this is a very interesting problem to analyze, is to understand the location of these zeros. Let me make one final comment, promising I wouldn't make any more comments, which is the following. So in the work of Brothwick, he uses this formalism to extend the zeta function because it's the one that's available. And it actually gives you more than I've said. It proves that the zeta function is analytic, but in fact it does more than that, because not only are these operators trace class, but you have extra properties which say that the convergence is very fast. So in fact, if you wanted to numerically estimate this zeta function at some particular complex value, it's not so difficult to do. Your computer grinds away for a shorter period of time than it would using some other algorithm. And this is the basis of lots of different methods for computing things in dynamical systems. It started with Sutanovich when he was computing values for renormalization of unimodal maps. Various people used it to compute things like Hausdorff dimension of hyperbolic Julia sets and things like that. But it's a very sort of a versatile method for computing lots of different interesting numerical values and trying to get interesting things. You can, for example, also use it to compute integrals. Not so difficult. And one of my PhD students actually used it to compute some numerical values for Mahler measures, which were mentioned in the previous talk. They're not particularly better than anything else, but they're a different kind of method. So I would recommend to you to try and find out about Brothwick's preprint, because it's very entertaining and it gives a lot of insight into these methods. And I think I'll stop there. Thank you very much.